right, so I'm going to talk to you about Cham++. And I have 3 or 4 slide sets. What I tried to do today, since I've condensed it to a 1 hour, or tried to condense it to a 1 hour version, is basically I have more information in the slides than I will talk about. But for those of you interested in it, you would be able to fully use all the slides later on by reading them and so on. So if those of you are in the habit of reading every slide that comes in front of their eyes and feel really jittery if I move forward, well, be warned, I'm going to be skipping quite a few slides for that reason, for the reason I mentioned. So I think we don't need, for this group, a summary of challenges in parallel programming, but just to emphasize a couple of motivating points, the applications that we look at over the years, they're getting more sophisticated. They use things like adaptive refinement. They tend to be multi-module, multi-scale, multi-physics, and so on. And as an example, load imbalance is sometimes emerging as a huge problem, critical paths and other things. Now, strong scaling needs is another thing that's going on. By that I mean that applications, what happened over the years is that when you people developed an application, a new machine came along, the scientists then wanted to increase the resolution because they wanted to capture the full physics. And so a bigger machine was utilized by going to a bigger model, larger degrees of freedom, and so on. That trend is kind of coming to an end. People have adequate resolution, or if it is not adequate, it is inadequate only in the regions of interest. So if there's a storm passing through an area, you want more refinement there and things like that. And then there are fixed size problems that people would rather solve much faster than before. This, of course, makes it a harder problem. Sometimes people have a hard time understanding this concept when you write a paper about, let's say, an computational astronomy paper based on some n-body movement, and you say, we took a 2 billion particle simulation and ran it on a few 100,000 cores, as opposed to a 24 billion with similar efficiency. Well, people think 24 billion must be the harder problem. No, it's the 2 billion that's the harder problem, right? If you want to get good efficiency all the way. So people are actually solving more of these strong scale problems. And then the hardware, I'm sure you hear about exascale all the time. What's happening in future is that as we go from 22 nanometers to 14 nanometers and smaller, and as the power issues and energy and temperature issues become important, all kinds of variations come into picture in the hardware level. Static variations and dynamic variations. Some chips are just different than others. Some get hotter than the others quickly, and so on. And so all of these issues actually complicate. We have to deal with them in programs and in applications, then it complicates programming. So how are we going to deal with it? We don't, it's foolhardy to think that we're going to fully automate this process by letting you specify the program in a sequential Fortran program and auto-parallelize it to everything, and it will take care of everything else. But at the same time, it's not a good idea to put the full burden on the application developers too. What we seek, and that's a design philosophy in Cham++, is a good balance between the system and the application developers. So what is Cham++? Well, it's a approach to writing parallel programs. So it is an alternative to things like MPI, UPC, global arrays, Chapel, etc. But it is not an alternative to sequential languages such as C, C++, Java, and Fortran. In fact, you write C++ programs and you write Cham++ programs. And it represents then a style of writing parallel programs and a methodology for developing them. And it is backed by an adaptive runtime system. That's probably the key key component in Cham++ that differentiates it. And there's a whole ecosystem. It's a fairly mature system, been used for more than half a dozen applications and runs on all parallel machines that we know of. There's debugging tools, there's performance visualization tools, and so on. Well, so what is Cham++? Well, it's an object-oriented parallel programming system. So that object orientation has helped people in the broad industry to conquer, or at least deal with the complexity of programming. And we'd like to bring that view to parallel programming, not just by using C++, but by using the idea of objects in a parallel design. We identify the identities as a programmer, identify the entities being simulated, and then define objects and tasks around those entities. I think this will become much clearer when we talk about it in detail. And what about processors? Well, processors are not part of the ontology of a baseline Cham++ program. So you shouldn't be thinking in terms of processors anyways. As we go further, as Jim Belloc likes to put it, you should be thinking in terms of work, not workers. And MPI, if you look at MPI, one of the intuitive appeal of MPI is the fact that it's kind of anthropomorphic. You're thinking, I'm a processor, I do this, then I wait for that, then I send this. And it's actually nice in many ways, but it limits your freedoms in so many other dimensions that you don't want to think in terms of workers and the script for them as the program, but rather work and the script for that work. And then let the processor be someone else's concern, right? So the three principles in Cham++ are over-decomposition, migratability, and asynchrony. So over-decomposition is the idea. In parallel programming, you always are decomposing the computation into pieces, right? We just say, just do more of that. Break it down into smaller pieces. Pieces all the same. You don't break it down into a floating point number or something like that. Coarse-grained pieces, but many more than the sets of processors, cores, or nodes that you have. So this is not so hard. In fact, it's kind of easier, frees you away from thinking in a processor-centric manner. The second notion is that these pieces then are migratable across processors. What that means is that so these pieces, which could be work units or data units or some amalgams of those, the runtime system is free to move them from processor to processor as the program executes. What does that mean? That means as a programmer, you should never think about the place where the processor is. You should communicate with that object, right? The work unit or data unit, which in case of Cham++ is going to be a C++ object. And the consequence for the runtime system is that it needs to figure out, given a name, given an object name, it should be able to figure out where it lives. Okay, that's something that it should do. It should automate that and do it efficiently. And it does. Asynchronous is the next component. So you have many units, objects on each processor. They address each other via logical names. Now, and we'll see that the communication in Cham++ specifically is asynchronous method invocation, but as a general model, they could be communicating through messages or whatever, right? And there is, and so the question is, all these units that are sitting there on a processor ready to be executed because the data for them is there, who decides what runs next? Right? And there are two possible answers. The programmer orchestrates and says, okay, this we'll do this first, then that, then that. And the other one is we let the runtime system decide. That's the answer Cham++ chooses. The sequencing, the selection of which work to do next is left up to the system. You, of course, can influence it through priorities and sometimes more explicitly, but mostly through priorities assigned to these work units. So this is called message-driven execution. So we'll see it in a picture in a second. In Cham++, the over-decomposed entities are chars, which are C++ objects. They have methods, and some of the, oh, by the way, this is a good time to ask that question. How many of you have never programmed in C++? It's OK. All right, so that's quite a few. And for you, some of this terminology might not make sense. Let me just say that Cham++ has a way of has a Fortran interface. You write the parallel wrapper in Cham++, and then the rest of the sequential code can be in Fortran. But I'm going to take the viewpoint of a pure C++ programmer here. And so in C++, objects have subroutines that are called methods associated with that particular data, right? And some of these methods in Cham++ are designated as entry methods. That name goes back to some historical notions of what's an entry point in OS. But basically, that entry methods are methods that can be invoked by objects that may be on remote processors. Okay? So, those invocations are asynchronous. That means if I send an invocation towards an object, I don't wait for it. I just send an invocation towards that object, sort of like an MPI message, and I continue on doing my work. Right? So that's an asynchronous method invocation. At some point in future, that object will get that method invocation and execute it. These chars can be singleton, but they can also be organized into indexed collections. And those collections can be a 1D dense collection or 6D sparse collection and so on. So you can think of them as char arrays. When you talk about arrays, though, don't think of them as the data arrays of floating points. These are collections of chars, collections of objects. And chars are nothing but C++ objects with these that can take an entry method, that can take an asynchronous method invocation from a remote processor. So if I keep using the word char, don't be confused, it's just a C++ object. All right. And like I said, they communicate via asynchronous method invocation. Suppose you invoke a method foo in an object at index I in the collection A. You would write a square bracket I dot foo and give it some parameters. What happens internally? The orange object on the left is the one that's sending that method invocation. The system first takes those parameters and marshals them into a packet of information, a message, and that's the blue thing there. And that blue thing, instead of sending that a.foo, the programmer doesn't know where it lives, so that packet actually is given to the runtime system, which figures out where it lives and just puts it in the scheduler's queue on that processor, right? At some point in future, that second processor on the right will get to that and then say, oh, that's meant for that object, and it hasn't migrated out of here yet. If it has, it will forward it where it goes. And so it will invoke the method in it, let that method run to completion. So it's not going to block for anything, at least in the baseline charm model. That guy is not going to block. Method runs to completion, control comes back to the scheduler, whereupon it picks up the next method invocation sitting in his queue, right? So any question on that model so far? Yes?
Why do you call it char?
Char?
Char is
The language char++ or the object char?
the object.
Object char. This actually is a long, old thing. Maybe I can tell you more about it. But basically, it's a word we took from a project called ReadyFlow project that Bob Keller did many years ago. Rusty might remember it. And this was a parallel list project. One of his students was a professor next door to me. And so we just, to kind of honor that project, we picked that word. Char means chore. It's an old English for chore, a piece of work. Okay. All right. So now, if you have the same situation on many processors, right, and there are all kinds of objects, but actually those objects are doing more or less amount of work compared with each other, right? And so the runtime system can observe that and say, hey, some of these objects, processors are overloaded. Let's move these objects around without the programmer having to really know that they moved, right? And although if you want to know, there are ways in which you will know so that you can take some different types of actions. But basically, fundamentally, your programming model is that you don't know where the objects are. And so the system will take care of the fact of moving them to reasonable places, right?
Not taking into account the communication.
Yes. Yes. So that's why I said the runtime system's responsibility to figure out which objects are talking to which, how much computation load. Notice that it's involved in scheduling, so it knows the execution time associated with an object. It's involved in communication, mediating the communication, finding where that object is. So it knows how many bytes did you talk and how many times to which object. So, these foundation of asynchrony over decomposition migratability, you build on top of that with introspection and adaptivity, and you get an adaptive runtime system, which can do various things like dynamic load balancing and so on and so forth. I'll talk about some of those things later, so I won't enumerate those here. Yeah, so this is just a pictorial representation of all kinds of capabilities that are enabled by those concepts. We'll be going through those, some of those next and some of them later on. So the first thing is, if you think about many core, accelerator, all kinds of stuff that is coming around, one of the advantages of objects is that objects connote locality. So what's inside my object, I can directly access. What's outside my object, I need to do an asynchronous method invocation for. And that fact structures your program naturally for locality. On top of it, message-driven execution that you saw means that the scheduler can peek at the queue and know what are the next few things that you're going to run. As a result, it can actually pick prefetch objects. Oh, the next three things are these objects. this data is being accessed, this method is going to be executed. Therefore, I can start prefetching the next two while I start executing the one that I already prefetched, right? And so that ability turns out you can do out of core based on that, variety of things based on that. If you look at how you do communication, most MPI applications, you do compute, then you communicate, then you compute, then you communicate, and then you have this gap in the middle that you say, oh, I'm spending so much time on communication, and then you work hard to reduce the communication time from 40% to maybe 10%. What you achieved is 90% of the time your network is not being used, and then you go to the vendor and say, make my network faster. Instead, if you have over-decomposed the program, then your communication naturally spreads over your time step. And so you're utilizing the network more efficiently, effectively, and on top of it, you get you're not waiting for communication. You're getting a very natural, without having to program it, natural overlap of communication and computation. Now, you tend to decompose in today's in standard methodology today two processors, but this has many problems. Let me just pick an example, right? So you have a rocket simulation. You're doing solids and fluids, right? And well, you partition the solids using the unstructured mesh partitioner. You partition the fluids using some other partitioner, and then 17th partition of fluid and 17th of solid are put on processor 17 because their partitioners call them 17th. Right? No better reason than that. Well, with objects, you actually have two separate collections, don't even have to be of the same size, and then the runtime system is going to figure out who talks to whom and accordingly move them closer to each other. I think I'll skip the composite. Well, it's kind of an important point, so let me just show the picture of it. One of the ways in which you deal with multiple modules today is if you have a module B and C that are both concurrent, that is, they can both get started, then the parent module A will fire B, and then then it can fire C at the same time. Which one should it do first? Well, the typical solution is to fire B first. Partition the processors, you do B, you do C, or say, let's all do B first and let's all do C after that, right? But the other solution that becomes possible with something like Cham++ is the fact that you can initiate both of those modules. They can start communicating their messages, and then scheduling becomes based on the availability of data. They interleave their execution, thereby overlapping useful idle time in one module with useful computation from the other. It's pretty hard to do with existing methodologies. Not impossible, nothing is impossible, but it's hard to do. So Cham++ is a way of parallel programming that's based on all these concepts. I think I'm a little low on time here, so I will skip to the syntax. Okay, so now we get from all these lofty ideas to nitty-gritty syntax, and indeed there is a little bit of a learning curve there, but we'll do an overview now. So let's start with a hello world example, right? All right, so this is a Cham++ hello program. Without too much explanation, I'm just going to show that program and then explain the components in some more detail. So you have a CI file in addition to the normal C++ file and the .h file. You have a CI file, which is an interface file. In that file, you describe your entry methods and their chars entry methods and their basic signatures, right? So in this case, there is only a char called main, and actually, there is a char. This char is designated a main char. You can have more than one main chars. Main char is the one that, so the whole program execution begins by creation of one object on one processor somewhere, right? And that object is a main char. An instance of the main char is created somewhere. That object may create other collections and objects, and that's how the program begins. So you designate a main char by calling it a main char here, and every .ci file typically is a module. You can have more than one, but let's say just have one module, and you have to name that module. And then you have a .c++ file, which has the actual C++ definition of that class, in this case class main, and we'll see what it inherits from and so on later. Notice that it is doing a printout. Those of you know C++, do you say something odd about that printing? CK out, not cout. Okay, so that's our stream, output stream that we can manage and do useful things with. So you CK out instead of cout, and then not call exit, but call CK exit. And notice also this decal.h at the top and def.h at the bottom here, right? That and that. So we'll come back to those things in a second. Now, well, I'll skip that example. It doesn't do much. So the file structure is that you have an interface file, which we'll describe, .ci. You run the charm compiler called charmc on it, and you get the decal and def files, which you include in your .c program. If you have a .h and .c or .cpp, then you put the decal.h file that was generated at the top of the .h. Those are the declarations that the charm translator generated based on the interfaces, and then definitions of those are at the bottom in the def.h file. Basically, what are those things? Well, those are, I said, oh, method invocation is automatically packaged and sent. Well, how does it do the packaging? There has to be a code generated, and that code is generated based on the .ci file, which you get to use, and so you need to put it in the def.h there, right? So, and then of course you compile them as usual. So basic workflow is charmc hello.ci, charmc -c hello.c, which now incorporated the decal and def in there and generated the object, and then charmc -o hello.o. Of course, the last two can be combined if you want, as usual. And for running it, you just, this varies from machine to machine. So we'll tell you about BlueJean what the command is. But you basically, the basic command on networks of workstations, for example, is charmrun plus P7 number of processors, how many you want to run it on, and the name of the program, right? All right, we saw this already. So what is interface? Well, Charm++ programs are organized as a collection of modules. Each module can have one or more chars in it. And the module that contains the main char has to be declared as the main module. Okay, so we don't like parsing innovations. For those of you in computer science, we try to keep things as simple as possible, which is why you'll see that we don't touch C++ files at all. Charm++ is a pretty old language. Nowadays, you can probably parse C++ better, but even then, it's not a wise idea. So we do all our parsing in a simple .ci file. C++ file we don't look at, we just use that. And so main char, the module must be called main module. And so the basic syntax for modules is, the basic syntax of the .ci file is module, my module, open curly, close curly. And the module can be main module. And within those curly braces, you put char definitions with only their signatures. So, so each entry method, so for example, in the .ci file, if you have my char, then the system is going to create a variety of classes. One of those classes is going to be cbase underscore mychar. Okay? And your class mychar in here must inherit from that cbase mychar. So you declare mychar, you told the system about it, and then you must inherit from it. Okay? So these are the details that you have to do that you get used to and those create a little bit of a learning curve, but it's just boilerplate. You just, every time you declare a char class, you must inherit from its base class, right? So that you get certain variables inherited and that you can use that we'll learn about, right? Now, in the .ci file, those entry methods inside the ... are declared like so: entry, name of the entry method, and then parameters in a slightly stylized syntax. They all should be void return, because remember, asynchronous method invocations don't return anything. Therefore, their type should be void, except for, of course, the constructor. And so the constructor is entry mychar. And then others are entry void foo, entry void bar, some parameter, and so on. And correspondingly in the .c file, if you're used to writing defining the methods with : notation, then we say mychar : foo and write the code there as before, mychar : bar int param and write the code there. So that part is just like regular C++. So okay, so I gave you a lot of syntax. Really basic from my point of view, but really a lot of syntax for someone new to it. Any questions here? Yes.
So where the name the cbase in the previous slide come from?
Oh, that's just a name of a class that the system generated. So it's a base class from which you are inheriting, right? And so if you declare a char class C, then mybase underscore C is a class that system generates. It has some public data members and private data members and so
Are there other ones it generates, or just?
it generates quite a few of them. It generates a proxy class. It generates a proxy class is one. We'll learn about that in a minute. But you need to know about only a couple of them, and they just have to be plunked down in places in sort of obvious ways. Okay. So execution begins with by installing, constructing the main char, and giving to it as a parameter all the arguments that came from command line. They come in the form of a for historical reasons, they come in the form of a called ck-arg message, which is a struct containing 2 pointers, argv and argc. Okay. So now, if you want to create a char, you say, you don't just say new, you say ck-new. So suppose my char class was my char, then I'm calling the ck-new method on the proxy of that char. Proxy is another method that the system created. You don't have to, right now, just take my word for it. To create a char of type my char, you must say cproxy underscore my char colon ck-new and give it the normal constructor argument that you declared it with. Okay? Why not normal new? A normal new will construct a local sequential C++ object. You want this object to be viewable by other objects. You want them to be able to send method invocations to it. So this proxy ck-new actually generates a object that is called proxy, which is a proxy to that object. That object might exist on some remote processor. You don't even know where this object went, right? You just created it. At some point in future, that object will be created on some processor. But you have a handle to it. That's the proxy to it, right? And to that proxy, you treat that proxy as if it were that object. So you can invoke any method that entry method that you'd invoke on the actual object. You can invoke it on the proxy, and the proxy will take it and package it and send it to the real place. You deal with the proxy here, right? That's the purpose of the proxy, is to be a proxy for the real object which lives elsewhere, right? And so you create this proxy, and then so if you have a proxy to an object, here is a method called foobar2, which happens to be given as a parameter, it's given a variable main, which is of type proxy underscore main, right? And so I can use that proxy. If I happen to know that the main object, the main class has a method called foo, then foobar2 can actually call foo on the main as if it's just an object, right? Just a local object. Yes?
So the proxy here is a pointer to the object you created? Or?
Proxy is you can think of it as an abstraction of a pointer. It's a handle to that object. Right? A regular C++ pointer is valid only within your address space. Later on, you'll hear in the next talk about pointers that are valid across processors in UPC. In Cham++, it's not a pointer, it's a proxy. If you want an object and you want to interact with it from asynchronously from potentially different processor, then you have to interact with it through its proxy, right? So instead of new, you call ck-new. Instead of new giving you an object pointer, ck-new gives you a proxy, and then you can invoke the method on the proxy. That makes sense? Yes.
Do you have a single proxy, or you can have multiple proxies pointing to the same?
You can have, you can copy the proxy, call it a different name. It's still the same proxy, and you can pass them around to different processors, right? But yeah, yes.
So that's kind of interesting. So you're not using like the default constructor.
No, we're not. Yeah, we're not. So the real constructor of the object will be called when that object is installed. At that point, your parameters will be used, and your constructor, just regular C++ constructor, will be called on the processor where this object is being installed. Right? Okay. Yes?
Can you bring one slide to the back? So the proxy here, you mean like we can just see proxy and the proxy changing it, and thus will make different objects?
cproxy underscore mychar is only a type name, right? ck-new creates an object and gives you a proxy back. If you are an object, a char, and you want to find what your proxy is so that you can give it to someone, you can do that by another function. You can say this proxy, the variable this proxy, just like variable this is a pointer to yourself, this proxy is a proxy to myself. And then you can take this proxy and copy it into a parameter and send it to someone else. Now they have your proxy, and they can communicate to you through that.
The constructions arguments are actually for the proxy, not for the actual object.
The constructor arguments are for the object, the same, because why would you do anything else? So you're just giving them to the proxy, and then the proxy will take it and you're right, and send it to the. But there is one. Well, okay. Order one answer. Yes, that's correct. Okay. All right. Termination. How does a program terminate? You can call exit, right? Because then what will happen? Remember, there are all those message-driven schedulers sitting on every process saying, "Hey, my queue is empty, but maybe someday someone will send me a message." Right? And then it will keep on going there. You know this, I don't know how many of you read Hitchhiker's Guide to Galaxy, but there is a plane sitting on a tarmac for centuries there. And every few centuries, the robots wake you up and serve drinks and send you back in hibernation. Saying, people ask, what is going on? Well, we don't have napkins, so we're waiting for them. And, well, napkins, no, let's take off. And they say, no, civilizations will arise around us. They will eventually produce napkins, and then we'll go. All right? Well, these schedulers will sit there forever like that. So how do you terminate them? You have to tell them terminate, not just locally terminate. So you make a system called ckexit. You can make it from any object, any one call anywhere will propagate that information to all those schedulers and say, hey, it's time to terminate, and then it will do the cleanup. All right, so now let's look at this example in a little bit. Here you have a my module, which is a main module. It has a main char, and it also has a simple char, another char called simple, which happens to take 2 parameters, right? Okay, so here is the .c program corresponding. .ci we already saw, right? Any questions on that? You just have 2 char classes. These are not 2 chars, 2 char classes, and then each one has a constructor, and that's all it has, right? So the main char, what is it going to do? Well, first of all, you included mymodule.decal.h and mymodule.def.h at the top and the bottom, respectively. You don't have a .h file. Otherwise, you would put that in the top of this at the top of the .h file. You have a main class definition, which happens to have only one constructor. It is inheriting from this cbase_main, which is, where is the definition of cbase_main coming from? It is sitting inside of this. Where did it get there? In the decal file, it was created by, the declaration was created by the .ci file, using the .ci file by the Charm compiler. Then the main class, you first say hello world, and then you say, I'm going to, you're going to just print the argument. Let's skip past that. And you're going to just simply call cknew, or you're going to create an instance of the simple char by saying cproxy_simple : cknew, and you're giving it 12 and you're giving it pi. And so it's going to, that object when will get created, it will say area of a circle of radius x, which is the first parameter given to it, is radius. Did I do it wrong here? Pi r squared. No, that's correct. So that y is pi, which we are passing it for some reason, and then it just calls ckexit, right? A silly little program, but it's useful to show some things. So entry methods are invoked by calling the methods on proxies. So you say proxy.foo, proxy.bar. I think we have gone over that. Let me not. Okay, so. I think there is one semantic thing that you should understand. Given a particular char object, there may be 7 method invocations waiting for it. Only one of them will execute at a time. In practice, that means the char itself is anchored to a core or a node, so that it's not going to be the case that 2 different cores or nodes are executing 2 different methods in method invocation sent to that char, okay? So that is simply enforced by having it anchored to a core. All right. So here I have a proxy. I created an object called my char, and I'm invoking the method foo on it, and I'm invoking the method bar on it, right? So foo prints foo executes, and bar prints bar execute with param such and such. What order will the prints happen? what order will you see them on your screen? And the answer is, we don't know, right? Charm++ does not enforce the order of messages between objects even, between a same pair of objects, because it's, after all, if I send a message to you and you send something to you and then we have another path to going to the other processor, even MPI cannot guarantee ordering anyways. So, and it's an extra overhead thing, and we say we're not going to pay that overhead until and unless we need to, and then in that case we'll have constructs for enforcing that order, right? So the baseline is highly asynchronous model. So even the execution that I sent first and then I send the second method invocation, they may cross each other in the queue and then they execute in a different order, right? Okay, so so that's the point of that. Now we kind of make our simple object a little more complicated, okay? So the main char is the same, well, slightly different. The simple char has a method now called findArea, and that findArea method is going to given a radius and a Boolean. This time we assume that it knows what pi is. No, it should have been given, oh, the pi was passed to it when it was constructed right here. And then when this findArea is constructed, called is going to then print the area. And then if the Boolean is done is true, then it's going to call ckexit and tell the scheduler, hey, shut everything down. Whereas the main object creates this object and in a loop 10 times calls, invokes the method findArea on sim. It's an asynchronous method invocation because you're invoking it on the proxy. What will happen? Does the program execute correctly, or if there is a bug, what is it?
Are you guaranteed all iterations will happen before it exits?
Yeah, that's what we would like to have happen, right? We would like to make sure all 10 iterations happen and then the program exits. But that won't be the case because the messages may cross each other in the network or in the queues. And so you're assuming here, this code implicitly is assuming by the way it is doing the bool done is the last time I call this, I'm going to call it with true. All the previous 9 times, I'm going to call it with false. And I'm hoping that therefore this last call will reach there last and therefore will execute last. That's not true, right? And so this method of dealing with that synchrony is not right. Asynchrony is not right. You need to figure out a different way of structuring the program. So this asynchrony is one of the things that you have to get used to when you write charm programs. We'll learn hopefully briefly about a tool that helps you quite a bit with the asynchrony, but it's a fundamental concept that you should figure out a way of grappling with. Now, let's see. I'm going to bypass some, okay. I'm right there. So objects, I said, are usually in charm+ programs used by the science and engineering community. They are, we don't use singleton chars like I showed in the previous example. They're usually collections, right? You're doing some data decomposition of your domain, and so then each piece of the domain, which may be chunky piece, that becomes an object, and so you have a collection of those, right? And so so you can actually get index collections, and those can be 1D, 2D, or up to 7D, I believe, and they can be sparse or dense. That means you can have a char array whose indices go from 0 to 1 billion, but only 10,000 of them exist, right? Some random 10,000 members exist. That's a sparse collection. All right. So here is an example of this example and its small extension will pretty much capture everything that you need to know about writing charm programs, right? And so here you have a main module called ARR, for char arrays, I guess. And then there is a main char in it. It just has the constructor. And then it has a hello char in it. Instead of calling it char hello, this class's definition is array square bracket 1D hello. That means it's a collection of chars which is organized into a one-dimensional collection, right? And then that has, just like chars, you have entry method called hello, which is the constructor, and another entry method called print hello, which is going to do some printing. Again, has no parameters in this case. It's just going to print hello, right? So array square bracket 1D is maybe somewhat awkward way of saying it's a collection of objects which are one-dimensional, which use one-dimensional indexing. In the .c file, And this is another style that you can write. Instead of class main, you can write struct main. That's just a C++ ism that some of my students like. So struct main, subclass of cbase_main, and that has only one method, the main method with argc and argv. And the argv square bracket 1 is going to, and I think I'm not doing any good error checking here, but argv square bracket 1 is going to tell me, hey, I need to create a collection of size 17, or whatever the number is passed to me on the command line. And so I just create cproxy_hello : ck new. That's just like before, but the fact that this is an array means that I need to provide a array size as a parameter. It's a two. Why is it twice? Well, okay. One of those two is the actual array size. The other one is a constructor parameter. Now, I'm forgetting now which order it is, but the last parameter, let's assume, is the size of the array that is being created, and the first parameter is the, then you can have several parameters that are just arguments to the constructor. So every object that is created will get the same constructor arguments. Any differentiation between them will come based on their index. And so now the hello class, you created that, you have created a proxy. This is a proxy to the whole collection, not a proxy to one object, but proxy to the whole collection, right? And so when you say p square bracket 0, that gives you a proxy that specializes that proxy to point to one of the objects, right? So you can also not put square bracket 0 here and just say p dot print hello, which will mean what? Can you guess? If you don't put square bracket anything, p is the proxy to the whole collection. P square bracket 0 dot hello means send the print hello method invocation to the 0th object of the collection. And p dot print hello would have meant broadcast to every one of them, right? Okay, so then there is a hello class, and the hello class has the print hello method. Ignore this ck migrate message constructor for now. That's for load balancing purposes, and it's just something that you, for now, it's just a boilerplate that you add. Print hello method will print something and say hello from object such and such, and you can find what processor you are on, and you can find your index. I mentioned this proxy, now there is also this index. And since it's a 1D array, you just have this index. It will tell you which your object serial number 23 or whatever. And then you simply print that hello, and then if you are not the last guy, then you send it to the next one, right? This index plus 1, print hello. That's all that this does. So now you have a method invocation based on this proxy, remember, is the proxy to the whole array. And so this proxy, you specialize it by saying square bracket the index, and so you send the invocation towards the next object in the collection, right? Right. Yes.
So how does it know this proxy? How's that in the scope?
Oh, this proxy is inherited from cbase_hello. So that's the utility of having that base class. The base class gives you those variables such as this index, right? Okay. So right away, we can introduce, Chum++ has a very nice performance visualization system. And to use it, all that you have to do is in the make file, in the link step, you just say -trace mode projections, and it will generate a log for every processor. And then you can view the log in a variety of ways, analyze the log. Here, I have only shown the timeline. And you can see that it has done a block mapping of that array, and the messages are going back and forward through this, and it's terminating here, and so on. So you can zoom in various ways. You can mouse over, and you find a lot of interesting information. And you can do, we're not going to talk about projections, but you can do fairly sophisticated analysis through that. I think you can do similar stuff with 2D arrays. We're not going to get into the syntax, so I'll skip that. So for 1D, it is this index. For 2D, it is this index.x and this index.y. And similar things for higher dimensions. You can find your own index. Yes?
So in the hello case that you mentioned before, it looks like it calls each of the different hellos in the array in sequence.
Yeah, yeah.
So does that happen in parallel still because of how?
You could, this is actually a really neat thing. In this case, that's so because you just said this proxy, wherever you get the message, you send it to the next guy, this index plus 1. That behavior made that chain, right? Suppose you start here and say, hey, let's start a chain at 0. And then right after that, you say p square bracket 23 dot print hello, right? 2 rings will start, and they will work perfectly well concurrently, overlapping with each other on processors, right? Or if instead of this index plus 1, if you say this index plus 17 modulo the array size, you will get a different type of a chain. And again, you can have multiple chains running at the same time, multiple objects, multiple collections overlapping at the same time. So it's kind of a beautiful thing to watch if you do projections, just to get an idea of what asynchrony and automatic overlap can do. Right?
So within that method, it's sequential, but you can start different parallel iterations.
Oh yeah, this code, this example is not at all parallel. This is completely sequential example. It's like a long chain. You would never write a parallel program that behaves like this, right? But this is just an example of how to do method invocations, right? You could, for example, write a ring program where everyone sends a message to the next guy. That will be nicely parallel. Yeah. But this is just to show the mechanism of how to do method invocations. Let me skip past 2. So to support this stuff, well, actually, the runtime has to figure out, given a collection and given an index, what processor it lives on. It uses a distributed directory very effectively and a very nice algorithm for effectively keeping track of that. You can actually control the initial mapping if you want. But the point is you can play with different mappings, but the application logic doesn't change. You can express the application logic in terms of these logical entities, which are the objects, and then do the mapping or dynamic load balancing orthogonally. Let me just talk about an example for how broadcasts are done. That's very obvious. I told you already. So instead of naming an index, if you just not mention an index for a collection, then the invocation goes to every object. Reductions are kind of more interesting. So each object calls a contribute, and the result of that, adding up those contributions are sent to some place of your choice, a callback of your choice. So you get to name a callback, and that's where it will go. In this particular case, for reductions, you actually tag the entry method with a tag that says, hey, this is a target of reduction. Now, the element method, which I'm going to quickly show, is going to do this. I mean, this is probably not visible here, so I don't know whether it's worth. Can you see it towards the back? Kind of, okay. I think I can actually zoom, okay. Okay, so this part here is where we are contributing. We are saying we are constructing a callback. The callback says it's for the main proxy. How do I get the main proxy? When I was constructed, my parent gave me its proxy. Main constructed me and gave me its proxy. And so I have the proxy to the main, and so I name it here. The first parameter is the entry method of that, expressed in a certain way, CK reduction target main done. So that's main object done method. And then I contribute the particular integer, which is my index, as an example. And then that reduction result will go to this callback, which is a particular object, main object there, which will say, OK, I got it, and will print it and call CK exit. So notice that in between, you are free to do other stuff. So contribute. Now, of course, MPI, the new MPI has asynchronous reductions, but this is what Champ++ has from the beginning. Contribute isn't connected with where the flow continues afterwards. The flow can continue with other method invocations and so on. At some point in future, the result of the reduction is available somewhere via a method invocation or a broadcast even, and then that you can continue using that. If you want to wait for that, you can make the computation wait for that, but you don't have to, right? Okay, let's zoom in. Okay, so I think that's all I want to say about this. Let's try and see. I think the next section I had here is called structure dagger, which is completely going to be omitted. So just in fairness, I will try to. I spent a lot of time making this section work well, so I will just introduce you with 2 or 3 slides. So as we described Champ++ so far, it's very reactive. You can write all kinds of very interesting programs with this, but it's very reactive. What do I mean by that? An object is described in the following way. Say, hey, I have these methods. If someone were to invoke this method, I will do this. If someone were to invoke that method, I will do that. But then you say, yeah, I understand, but what is your normal life cycle? What do you do? Right? This is what I will do if I get that, but there is something that you actually naturally do. That life cycle is not captured directly. You have to look inside the program, and then of course the life cycle is there, but it's not captured very directly. And structure diagram notation tries to capture that by a script, by writing a script for a char, which is kind of like a run method. If you know Java, you can write a run method for an object in a script, basically. And that kind of restores a little bit of MPI-ish flavor to it, but it's per object, not processor, right? This object's life cycle is described by its run. Typically, there is only one method called run, but you don't have to. You can have multiple methods there. And here, the sum method is saying, oh, when this entry method is called, I will do block 1. After that, when this method 2 is called, I will do block 2. And after that, I will do block 3. There is a sequencing, and there is waiting. Essentially, the when is basically like a receive, except nothing actually blocks and waits, okay? So it's only the object that's waiting there. Even the object's other methods are free to execute, but this particular flow within this object will continue only when the method comes. If method 2 comes first, method 1 will be, it will be buffered until method 1 arrives, and then it will do the right thing. And this, in this notation, there is, you can embed sequential C++ code by calling it serial. Those you can think of them as tasks that are done when method invocations come. And then you can write the standard if then else, while, and for loops. You can do interesting things like overlaps, but we won't get too much into that. I will just show you one example without too much explanation, but I will just, so this is a 5-point stencil that you probably, is a very popular example. And we've decided to do a very simple 1D decomposition of that. So every processor, every object rather, owns a strip, a block, a strip of values. And so it needs to communicate, because the computation 5-point stencil involves 4 neighboring values, up, down, left, right. Left, right I do have, but up, down values I may not have. And so I need to exchange the ghost layers from the top and bottom. Right? Everyone familiar with that concept of ghost layers? Okay. So now, this is how you will express that in Charm++. You have a main module. It has a main char, and it has a Jacobi char, which has a receive ghost method and a reduction target method, which is, you're going to test convergence, let's say, every iteration. And then you have a run method, which is a structure diagram method. So the code for the run method is shown here. It has those blue things, which are sequential blocks of code, right, that will execute. And then you have the dependencies on messages in the rest of the code. So basically, you're saying, while it is not converged, and you're talking about one object, first send a message up to the top guy, one to the bottom guy. Let's assume that it wraps around for simplicity. And then wait for this code is saying for I message going from 0 to whatever. When that message comes, any message matching that comes, then execute, copy that message data, ghosts data here into your data structure. And then do the work and check local convergence in the conv variable, and then contribute this, whether it's locally converged or not, into a reduction, and you wait for, then when the result of that convergence is back, you continue or exit. Right? That's kind of the basic logic of it. So now you can see a little bit of an order in terms of synchrony is restored, but you actually have still highly asynchronous flow between objects, and within the object, you actually can restore asynchrony in a variety of different ways too. So this notation turns out to be very useful when you are programming with Charm++. And you can add things like load balancing. The only difference in the previous slide and this slide is the last line, okay? There. If every k iterations I'm doing load balancing, if it is a load balancing period, I just make a call. We are not going to learn the details of the call. It's called @sync. And then you wake up on some other processor, potentially, because load balancer moved you. And at that point, you resume from sync method will be called. When that is called, you continue execution here, do nothing, and go on to the next iteration. So doing load balancing is a matter of as simple as just putting that one line there. There are a couple of more details, but we'll skip them here, right? Doing asynchronous reductions is another slide, but I will skip that slide because I want to get to a little bit of a design issue. So charm philosophy is let the programmer decompose their work into coarse-grained entities. But it's important to understand that what I mean by coarse-grained entities, so for example, to take an example that's like 12-year-old, instead of decomposing this unstructured mesh for some crack propagation problem into 16 pieces for 16 processors, this particular user decomposed into 128 chunks and spread them over 16 processors. So we could do load balancing as elements turned from elastic to plastic. Another example in molecular dynamics, NAMD is our well-known program written in Charm++ on blue waters with 100 million atom simulation. There were 5.5 million Chares objects spread on 128K cores or 4K nodes, right? That's one example. Here is another example. This is a Brazilian weather simulation code called BRAMS that was ported to Charm++. And here, there are, instead of using 64 work units, as the storm moves, there is a load imbalance. We use 1,024 work units spread over 64 processors. So this is actually what's happening is that as the grain size is very tiny, you get high overhead. You don't want to be in that region, but there's a big, broad region that you can be where you get pretty good performance. So setting the grain size is maybe a little bit of an art, but not that difficult because you can parameterize it, and there is a wide latitude in selecting the grain size. So I'll skip past the theory, and I just want to show, if I have 2 minutes or 3, I want to just show some examples of applications done using Charm++, not so much as the brag points, although part of it is that, but mainly to see the structure in terms of the objects, right? NAMD is the molecular dynamics application, and basically we decompose the atoms into cubes, shown here as squares, and that's one collection of objects. But we also said for every pair of nearby objects, for calculating the pairwise forces, Coulomb forces that are within the cutoff radius, we postulated these purple objects. So there are two object collections here. And it turns out for long-range forces, you need a particle mesh AWOLD, and for bonded forces, you need another collection. So you have like 5 different collections of objects, and the whole program is expressed in terms of these 5 collections. That design was done in 1995 or so in a 12-node HP cluster, and it continues on today till blue water. So once you design stuff in terms of the object, your design is sturdy. It lasts for a long time. Okay, so these points are going to show that it has, of course, scaled to 500,000 cores or more. Changa is our other application, which is an astronomy application, N-body gravity solver with SPH for smooth particle hydrodynamics. And here, the nice thing is that you decompose the computation into arc-tree objects, and each element, each leaf of that arc-tree, not really all the way down, each subtree shown in red there, red triangle, is an object, and the communication is expressed in terms of the bit vector that represents that position of that object in the tree, and it turns out that then the system can do pretty reasonable load balancing with that and get benefits of the geometry that arc-tree gives you. Skip over the details of that, and this has scaled to 500,000 cores as well. There is an application for simulation, agent-based simulation of epidemics done by Madhav Marathe and Keith Bissett at Virginia Tech, using Charm++. I'll skip past that. One of the new ones, well, one of the old ones that we have that's been revived now is OpenAtom, which is a quantum chemistry application. And the nice thing about that is this picture. You have a dozen different collections of objects, each with tens of thousands of objects. And mapping and orchestration between them gives you significant benefits. So I'll skip past all of that. We have a collection of mini apps, which is a useful thing to browse and look at for understanding Charm++. And there is a book now that has all the many of these applications. I want to mention one point, if I can. So if you look at cooling energy, right? So you have a problem, which is you want to save cooling energy in a data center. How do you save cooling energy? It's very easy. Walk up to the thermostat, increase the temperature. You save the cooling energy. Why don't you do that? Well, your processor cores will start burning down. Well, the runtime system can monitor the temperature, and if you find that a chip is hot, it can reduce its frequency. All right, great. But you understand for parallel programming now, it's tightly coupled thing, and some processors slowing down means everyone is going to slow down. So one processor slowed down by 40%, the whole application is going to slow down by 40%. Well, not a problem. We can just migrate objects away from that slowed down processor by doing a rate-aware load balancer, and we restore back the temperature is okay, the load balance is okay, the performance is okay, and you save the cooling energy. So that's the kind of stuff that you can do with Champ++. I'll stop with that. Yes.
So you have any examples of maybe a previous version of one of these that were using a traditional MPI approach and migrated to Term?
The Episim is an example. The agent-based simulation that I mentioned, that's using that. The other example is kind of interesting. Chambo is written in MPI. It's not converted to Champ++, but at some point, and for some particular application that they have, it turned out the sorting step was a problem. And so the sorting step was replaced by a Champ++ module for doing sorting. So MPI and Champ++ can interoperate.